Good morning. My name is Samuel Boone. I'm a senior research fellow in tectonics and thermochronology at the University of Melbourne and the University of Adelaide in Australia. But today I'll be speaking to you on behalf of the AusGeochem Geochemistry Network. This is actually a presentation that I recently gave at the IODP FUTURE DEEP workshop in Hobart, Australia in early April, in which I spoke about this open access data platform called AusGeochem, which the AGN has developed in collaboration with Lithodat, who I'll talk a bit more about the collaboration in a moment. This talk essentially spends about the first 2/3 talking about this platform and its pretty exciting functionalities. And then the last bit talks about its potential use as an IODP dual core collections archive, or digital archive, and virtual exploration tool. And before I get going, I'd like to acknowledge the traditional custodians of the land on which I'm presenting from, which are the Wurundjeri people of the Kulin Nation, and I pay my respect to their elders past and present. So the AusGeochem platform is a web-hosted open access data platform, specifically targeting or aimed at servicing the geochemistry community. This is a global platform, both in its scope, the data can be from anywhere on the globe, as well as this is the users. It's open access to anyone who wishes to use this anywhere on the planet. But we are we're not an Australian-funded entity, the AGN, that's behind this data platform. I'll tell you a bit more about that in a moment. And our initial motivation was to help service the Australian geochemistry community. So the platform is designed to essentially help foster a more fair geoscience data ecosystem, so essentially that's the purpose, is to make data more findable, accessible, interoperable, and reusable. So the AusGeochem Geochemistry Network, or AGN, whose behalf I'm speaking on today, we're a consortium of geochemistry laboratories from across Australia, and we're funded by AusGeochem, which is a government-funded geoscience research infrastructure provider. And we're we're based at 3 main nodes outside of our AusGeochem headquarters, and that's at Curtin University, where our current headquarters is at the moment, Macquarie University in Sydney, and the University of Melbourne. Last year, we expanded significantly to include 8 more universities across Australia that you can see here on the screen, as well as we had a couple of contributing partners join our ranks, including CSIRO and Museums Victoria, which is a science, it's a collection of museums based in Victoria, Australia. But in particular, we've worked very closely with the Melbourne Museum, which is Melbourne's premier science museum. So the AGN, comprised of a large group of expert geochemists from across Australia that specialize in a wide range of techniques. Our job is essentially to design these bespoke data models, each for different types of specific data, whether that be argon-argon or uranium-lead, major minor trace element geochemistry, etc. And we design the scope of the platform and its functionalities with the idea of best servicing the data producers and data users. But very importantly, we've partnered with Lithodat. This is a Melbourne-based geospatial data company based in Melbourne. And this partnership has been extremely fruitful. And essentially, they allow us, or they help make our dreams come true, in that they're the programming team behind the development of the software itself. So on face value, the AusGeochem platform may look very similar to a whole range of existing data portals, but we're distinctly different. And I'm certain that by the time that you finish viewing this presentation, that you'll agree that this is something entirely new, and I'll explain why that is. And there's a number of reasons that we're different than what currently exists. And first is how we actually essentially gather the data in the first place. This is an open access platform. It's designed that users actually import their own data at using AusGeochem as essentially a research tool. and then as a way to actually disseminate their data and make it publicly available. And we have a field app, which is available on Android at the moment. And this allows people to essentially gather information directly upon sample collection, whether that be sample location, lithology or mineral types, images, notes, and then basically, and this works offline. And then essentially, as soon as you're back online or back in phone connection, all of those sample metadata are automatically uploaded into the AusGeochem platform, meaning that when you get back to your office, you don't have to manually move all of that sample metadata into the field. We also work very closely with geochemistry data producers, the geochemistry labs themselves, to also streamline that data uploading workflow. We do this we have drag and drop functionalities, both for CSVs and Excel files, to help facilitate rapid data upload. And the platform, very importantly, also has an open application programming interface, or API, which essentially allows the platform to directly communicate with any other external client or software, meaning that if you have an existing database, say that's within your lab, we can migrate data automatically into AusGeochem using that API. We're also working with people such as IOLITE. This is an Australian-based laser ablation ICP-MS data reduction software company who have designed the IOLITE data reduction software. We're working with them to be able to auto-populate data right from the machine, essentially, once you've actually crunched your laser ablation data straight into the platform as well. So the first major difference is the way in which is the data workflow, essentially. We're trying to grab this data straight from the source and have users upload their own data as kind of a grassroots exercise to grow the database. Another absolutely key difference is that the database architecture behind AusGeochem platform is fully relational. And what that essentially means is that every single bit of data, whether that be the person that collected a sample, the location of that sample, any resulting geochemistry or geochronology analyses that are obtained for that sample, every single bit of data is connected to every other bit of data in the entire database. And what that enables us to do is to do some really powerful on-the-fly analytics, which I'll show you examples of in a moment. So let's get right into it. I'll show you the platform in action. And another major key difference is the way in which about the AusGeochem platform compared to all other existing data portals at the moment is that it's really designed to serve three different purposes. And the first is a sample registry. Essentially, this is a place that people can go upload their sample localities. It could be important sample archives, such as the geological collection at Museums Victoria, or potentially IODP with their core, really massive core library. Or it could be an individual lab. So let's look at the platform in action. There's a range of base maps. We can look at things in spherical projection or in a 2D Mercator projection. As you can see, it's really dynamic and very usable. Here we've turned on the light backdrop. Oh, sorry, excuse me, the topography backdrop. And we're looking at a whole range of samples and which have different types of associated analytical data, which you can see in the key in the top right. And now we're zooming in on the Alps in Europe. We're turned on a geology map that has different resolutions. What's amazing is that this platform is so dynamic that you can look at your samples into three-dimensional context, which is absolutely fantastic. And we can drape any DEM over any base layer over that DEM. For instance, I love being able to look at the geology map in 3 dimensions and see how the topography is controlled by the lithology and structural geology. We've also partnered with mindat.org. So we actually use their rock and mineral database behind our geosample metadata model, which means that when you tie a particular sample to a rock type, say, you can go find out more information about that through Mindat. We're also now a DataCite member, which means we can mint our own IGSNs for each individual sample. These are unique identifiers to ensure database integrity, but also that any individual sample can be essentially found through the platform. You can find out exactly where that particular sample is, and you can contact that person or lab or organization to see if you could collaborate them and use their sample material. We can then print out QR codes, or you could print out QR codes that you then put on your cores or your sample bags or your mounts or whatever it may be, which enables then someone to go use their camera phone, scan the QR code, it'll take them straight to the platform, and they can actually see what the geological and geospatial context of that sample was. So as I mentioned, it has a really dynamic user interface, allowing people to essentially explore the database in a geospatial context. So here we're looking at some samples material from East Africa in northern Tanzania. And we can scroll over to Australia. We can turn on other types of base map layers like gravity or magnetic, so you can actually look at the geophysical context in which these samples lie as well. So as I mentioned, we've recently partnered with Museums Victoria. They essentially approach us saying that they have this incredible, essentially research resource in this huge geological collection that they've collated over many years, that includes something like more than 50,000 rocks and mineral samples from around the world. And essentially we partnered with them to help them make their collection more discoverable. So now the entire, at least the digitized Museums Victoria collection is now available to be explored by anyone through the AusGeochem platform. We've associated images where they have them. You can find out information about who collected them, where they're collected. And ideally, people can now go digitally explore their collection. And then if they say, oh, these specimens are of interest to me in my research, I can contact them, or that person can contact them and request permission to use that sample for further analyses, which is excellent. So the second major, I guess, purpose that the AusGeochem, or function the AusGeochem platform serves, is as a data repository. So let's say someone has taken those samples and then done further analyses on these samples. We want those users to be able to put their data into the platform and make it so that it's more readily available to the public and can be explored geospatially. So we have a whole range of data models that that are already functioning in the platform, including major, minor, and trace element geochemistry, and we have bespoke plots and functionalities for each data type for people to explore those data. Here we also have a uranium-lead data model. We're looking at secondary ion probe mass spectrometry, uranium-lead in particular in this instance, but we have laser ablation uranium-lead coming on board very shortly. We also have a range of thermochronology techniques which we can accommodate, such as fission track and uranium thermal helium analyses. And again, for each of these, we have bespoke plots that are important for those communities. Here we're looking at some fission track data and on the fly generating a swath profile that shows you the relationships of sample ages and topography. Again, fission track analyses again here. And you can see that for each of these, we can filter by a range of things, by elevation, rock type, the type of analyses that we have, and then attributes of data as well, such as age, or in this case, standard deviation in those ages. And again, those filters are bespoke depending on the type of data, but it allows people to really interactively filter the database so they can play with, interact with, and extract the data that they're really interested in. We have a vitrinite reflectance model that hasn't been released to the public just yet. And the main reason I'm showing this is because for the IODP community, it's really important to view core data and their associated analyses. And just to show that we already have the capability to do that. Here we're looking at vitrinite reflectance data from a core off the northwest shelf of Australia. And again, we can grab a whole number of analyses. This is part of the Geoscience Australia vitrinite reflectance data collection, which we host. And we can grab a bunch of those samples on the fly and automatically pulls all of those analyses, something like 6,000 vitrinite reflectance analyses from across the northwest shelf of Australia, and we can see the relationship between data and depth. or a histogram of vitrinite reflectance rates. And the third function that the AusGeochem platform plays or provides is as a 4D, so 3D through time, geospatial data analysis tool. And I think this is the most exciting aspect of the platform. It's certainly why I'm so excited about being involved in this work. And it's also what sets it apart from anything that's ever existed prior to this. And the reason is because not only do we want people to be able to find the samples that are out there, which they could potentially use and collaborate on, we want them to be able to see the associated data and make those data publicly available so that to drive further science. But we also want the platform to actually serve as an analytical tool that kind of slots in to that research workflow. So as I mentioned, or alluded to, and you've seen a few examples of this, there's a number of on-the-fly or real-time data analytical tools. One of these are these dashboards. You can grab different collections of samples after you've filtered for the types of samples you want. We get a bunch of different plots, which they're interactive and they can be downloaded as SVGs to be used in your publications or reports. We have things like swath profiles, which we developed that on the fly. It takes, using the underlying DEM, it makes a swath profile and shows you the relationship between data and topography. So this is important, particularly for lower temperature systems like thermochronometers or nuclear cosmogenics or whatever the case may be. Here we're looking again at a different data dashboard for fission track analyses. So we have things like age versus mean track length, or MTL. This is an important parameter for the fission track community. Age versus elevation, radial plots, age histograms, all interactive. The other thing too is we have a table. Those data are now easily extracted, can be downloaded on the left, and we produce a reference list automatically from the selection that the user has made on the map to ensure that the actual data producers are being properly cited and they get the credit they deserve for producing these extremely valuable data. We also have other sorts of dynamic analytical tools, such as contouring, where you can essentially make spatial interpolations of different data parameters. Here we're interpolating fission track ages, I think, from Western Australia. We can toggle off whether we see the samples, the types of contouring. Here we're looking now at major, minor, and trace element geochemistry from an area in Western Australia. You can see you can click on one sample, find their individual data very readily, download those, no worries. But then we can also then use that contouring tool. Oh, sorry, here first we're filtering by different oxide concentrations. It's really fast and dynamic. And then we can then make these heat maps, quickly choose the parameters that we're interested in. We can change the sensitivity, the smoothing, the opacity. We can toggle on and off whether we want to see the samples. We can toggle the heat map. So really dynamic, powerful ways to interact with the data. Our most recent tool that we've implemented, and I think perhaps the most exciting, is our paleogeographic reconstruction tool. Now, this was developed in collaboration with the EarthBite group at the University of Sydney. And this is the group behind G-Plates, the plate tectonic modeling software. And essentially, using the PyGplates code, we're now enabling people to actually look at whatever geochemical analyses they're interested in their paleogeographic context, which is something completely new and extremely powerful. So here we're looking at apatite fission track data from, I guess, central Gondwana in around 546 million years ago, according to the model of Meredith et al. 2021. So you can select the paleogeographic reconstruction of your choosing, see how your data essentially rewind through time, see what their paleogeographic contexts were, and then all of those analytical tools still operate. We can grab a bunch of samples, look at how the distribution of data in a particular zone in central Gondwana in this particular instance. We can use that contouring map, and this is using their paleogeographic spatial relationship, which is extremely powerful, something very challenging to do prior to this tool, requiring you to essentially do a lot of work independently in using different softwares to start looking at these sorts of relationships. In the next few months, we're going to continue to bring on new data models. Within the next 2 months, we'll have the laser ablation, ICP-MS, uranium lead, and lutetium hafnium data models online, as well. And soon after that, we'll have argon-argon analyses. Later this year, we'll also have thermal history model capabilities, so that we can actually look at thermal history simulations using a lot of these types of geochemistry data, the results of which can then be viewed in their geospatial context. And through our work, we're continuing to expand the functionalities of the platform constantly. So please keep an eye on how the platform develops. So this last little bit, I'll just finish by showing, talking a bit about AusGeochem as a potential utility as an IODP digital library. I hope it's already clear that there's a lot of potential to host all types of geoscience data here and make them more discoverable and more interactive, essentially. And so I've made a bit of a mock-up about a particular scenario that could be used from an IODP standpoint. So here we have a core off the west coast of Australia. Let's say it's an IODP core, and at the time of collection, the well name, the sample type, the locality, its depth, any associated publications that come of it can all be linked to that sample geospatially, and images of, say, the drill cores and of even the people that have collected them can be linked to those sample localities. We could, of course, associate other types of data that might be important for that community if resourced to do so. So this could be downhole geophysical properties like gamma ray, density, porosity, etc. Now, let's say someone contacts IODP. They're really interested in working with this particular sample from this well, and they go back to their lab and they first acquire some oxide concentrations using electron probe microanalysis, and they upload those data. And now those are now freely available for people to interact with and play and cite, discoverable through the platform. They also then go and do some detrital zircon uranium lead analyses, and they see that there's a few smaller subpopulations, but they have this really prominent spike at about 2,700 million years ago. So that telling us a bit about potential sources of this sediment. We'll say in this instance, let's say it's an Eocene, Paleocene sandstone. And I'll also highlight that, again, these are mock-up data just to show the potential utility of this tool. But let's just say that this particular sandstone is really high in alumina. It's got a 14.7 weight% Al2O3 concentration. So the first thing someone may want to say is like, okay, well, what was the paleogeographic and context in which this particular sandstone was deposited? So we can rewind back to, let's say this sandstone was deposited 58 million years ago. We can rewind, we can choose the plate construction model of our choosing, rewind back to 58 million years. And here we've turned on the paleotopography data model of Cowdall 2021. And well, of course, it gives us an idea of what experts think the paleo environment was on the globe in different places at that time. So here, dark blue represents deep marine, lighter blue, shallow marine, green, subaerial, exposed land, and these browner and tan colors that we see in Antarctica to the south, representing areas of higher topography. So it looks like this sandstone, according to this paleogeographic model, was deposited on the shelf in Western Australia in a shallow marine environment. And so one potential understanding of its depositional history could be that, well, we've got high topography in Antarctica at that time, so we could be shedding material off of these mountains in Antarctica. But at this stage, we've already developed deep marine settings in between Australia and Antarctica, as seafloor spreading in the Southern Ocean is well and truly underway by this stage. So it's unlikely that we're getting detritus that's coming all the way north from Antarctica at this time and depositing off West Coast Australia. Instead, it's much more likely that our provenance source for these detritus is closer to home. That's probably coming off of the neighboring margin at that time. Okay, well, what can the uranium lead data tell us? Well, we saw before that detrital zircon uranium lead analyses from the sandstone said they had a really prominent peak at 2,700 million years. And we can use our multi-select tool of AusGeochem, look at all of the existing uranium lead data, or at least that's in the platform, from that neighboring margin at that time. And we see, well, it has a number of age populations. We see that this too also has a really prominent 2,700 million year age population in this region, suggesting that these basement rock terrains could have been detrital sources for this sandstone that deposited offshore at that time. Okay, let's try to narrow it down a bit further. We can then turn on our geochemistry tool. Again, look in this part of of Western Australia and use our contouring map, and we see we're looking at alumina. If we recall, those sandstones were high in alumina, and we see there is indeed a hotspot in kind of this central, I guess, Pilbara area where alumina values are quite high as well, suggesting that this is a likely, at least according to the geochemistry analyses, a likely provenance source for this for the sandstone that deposited offshore, and suggesting that there may have been a drainage system flowing to the west at that time from that region. Well, okay, that's really interesting. But is there anything that can tell us about how much erosion is occurring at this time from in that part of Western Australia as another way of testing this hypothesis? So here we can turn our apatite fission track analysis on. For those not familiar, apatite fission track analysis, is a type of thermochronology technique. And essentially what this allows us to do is constrain the thermal evolution of the crust, which in most cases can be converted to erosion rates through time. And so we can use our contouring map. And essentially what we see is that we have a quite disparate cooling history from Western Australia at that time, but everything's pretty old. We see from the ages that you can see on the top left there that apatite fission track ages from this area range between 128 and 422 million years. And what essentially this is telling us, because of the temperature sensitivity of this apatite fission track system, is that since in these blue areas where we have these youngest cooling histories, it basically gives us a limit of how much erosion has happened since those times. So that 128 million years is roughly telling us when rocks now exposed at the surface in those areas were exhumed through depths of 2 to 3 kilometers. So we know that since 128 million years, we've had no more than 2 to 3 kilometers of erosion in those areas. So depending on how thick that Paleocene sequence is offshore, that if it's really thick and we need huge amounts of eroded material to be shedding off of the continent in the Paleocene, well, then maybe we might need to look elsewhere. But if these successions are relatively thin, and 1 kilometer or less of denudation at the time is more than sufficient to provide that detritus, then our working hypothesis that the sediment source for our sandstones were shielded off Western Australia still holds. So I'll leave it there. Again, that mock-up was just using the functionalities that are currently in the platform. The platform, as I mentioned, is constantly getting new functionalities, new data types. And as we work with other communities, perhaps with the IODP community, we can bring in other types of data that are really important for those communities as well to answer the questions that they're really interested in. I thank you for your attention. I would encourage you to go on to ausgeochem.auscope.org.au to play around with the platform. Again, it's freely available to use to anyone in the world. And if you have any further questions, feel free to reach out to myself, Bryant Ware, the AGN coordinator, or Fabian Coleman, the Lithodat CEO.